last time we discussed about the relationship between the two types of frequency transforms, the one in the continuous domain, the other one in the discrete domain of time. So, we saw that if we know the analog domain frequency response, say something like this, if it is band limited, then if we can maintain a sampling frequency which is much higher than the maximum limit of the frequency in the band, then we can have the frequency domain response of the system for discrete time systems as a repetition of the same characteristics with a periodicity of 2 pi, where 2 pi corresponds to omega s, the sampling frequency. Okay. So, it is in terms of radian frequency, this is in terms of radians per second. You can always convert this to radian per second, that is analog frequency, and hence from a given characteristic like this, given frequency domain response in the discrete domain of time, we can always get back to the analog domain response by filtering this in the baseband and then taking inverse transform. So, Nyquist frequency criteria suggests that the sampling frequency should be at least 2 times the maximum frequency that is present in the signal. Now, for example, for music system 44.1 kilohertz is the frequency of sampling that we use for CD, compact disc. Then what do you want to really capture is a signal up to 20 kilohertz or so, 20 kilohertz or so, whereas for speech it is 8 kilohertz sampling frequency. That means, we want to capture within 4 kilohertz the frequencies of speech that will be within 4 kilohertz. This is for telephonic purpose, all right. For telephony we require 8 kilohertz of sampling. If you want, normally the frequency band is approximately up to 3.4 kilohertz that we want to capture. So, it is a little above twice this frequency. So, that is good enough. If you want to identify a person, very accurately, then we go a little above this. Quite often you must have observed, you must have experienced, when you receive a telephone call, you are not able to distinguish the voices of the speaker at the other end, all right, unless he introduces himself. Quite often we make mistakes. Okay. So, if you want to also recognize the voice, then we go for 22.05 kilohertz. That means, we want to go for a little higher band. As I told you yesterday, actually it is not suddenly coming to a drastic end at a particular frequency. We are truncating it by pre-filtering, otherwise it will be going tapering off like this to a larger value. So, where you are cutting this off will be ensuring the quality of the speech that you are recovering, all right. So, if you want to identify a person's voice, that means there are certain high frequency components, if you miss out you will not be able to identify. That is why for speech recognition, speaker recognition, we go for a little higher frequency of sampling. Okay. So, this will be little less than 11 kilohertz. Now, today we shall be taking up discrete Fourier transform. So, in discrete Fourier transform, what exactly you want to find out? When a sequence is of finite length, xn is a finite length, then the DTFT which we defined as summation xn e to the power minus j omega n, and from this DTFT we can recover the signal xn, which means what should I write? 1 by 2 pi, all right, e to the power plus j omega n d omega. So, you have to perform this integration. You have to know this in the continuous domain of frequency, all right. So, as I had mentioned, this x may be of this type, okay. So, you have to take the inverse transform of this to go from frequency domain to time domain. Since it is periodic, so in the time domain it will be discrete lines which will be xn, okay. Now, instead of computing this from this integral, can we realize this from some discrete values of this frequency domain representation? That is, we shall not take a continuous set of values, but we can take some discrete values of this. Can we compute xn from these discrete lines? If xn is a finite sequence, yes, then it is possible. If xn is finite, then xn can be recovered from only specific values of omega k, okay. We can realize xn. If xn is having a length of n, say 0 to n minus 1, x0 x1 up to xn minus 1, then we can take those many values, that is n number of values k varying from 0 to n minus 1. We can take only n number of frequencies and evaluate the function at those n number of frequencies, all right, and that is sufficient to define the function xn. You can always retrieve xn from not from the continuous function, but only from those n number of frequency domain representation. So, this we define. This is also very interesting. This will be the same expression xn e to the power minus j omega n, this we are omega into n, this we are evaluating earlier. We shall be taking only some specific values of k, omega equal to omega k. We take this as e to the power minus j 2 pi by n. We subdivide the entire angle of 2 pi into n number of equispaced points, all right. We call this basic operation of an angular shift as Wn. This capital W stands for unit, basic unit of the angular shift. See, e to the power minus j 2 pi by n is, if this is 2 pi, you divide into n equal parts, okay, like this. So, each of these will be corresponding to an angular shift of Wn. So, if I have 8 points, then Wn will be Wn1, that is 1 unit, will be e to the power minus j 2 pi by n. That is multiplying any quantity. If I say multiply xk by Wn1, it will mean xk multiplied by e to the power minus j, this n is now 8, 2 pi by 8. How much is it? 45 degree shift. So, it is xk into e to the power minus j pi by 4, which means xk multiplied by minus 0.707 minus j 0.707, 1 by root 2. That means the entire circle has been divided into 8 parts. All right. So, this is 45, 90, 135, 180 and so on. So, cosine of minus 45 degrees and sine of minus 45 degrees. So, that gave me this. So, it is basically a complex quantity that we are multiplying with the real term xk. All right. So, x, suppose you are given some values xn. So, let us take a very simple set of values 1, minus 1, 2, 3, 0, 1, 2, 1, 2, 3, 4, 5, 6, 7. Let us have one more value 1. For simplicity I have taken very simple values 1, 0, 2, 3. So, what will be capital X 0? We define, okay, before we go to that, x we are evaluating at e to the power j omega k at k equal to 0. We call this as capital X k at k equal to 0. So, that is capital X 0. Okay. Henceforth, in the transform domain we shall be denoting this, because there are only 8 for an 8 point sequence, there are only 8 frequency domain representation. So, I will call them as capital X0, X1, X2. All right. They are very similar to your Fourier harmonics. In the continuous domain you talk about harmonic terms. All right. They are also exactly similar to harmonics. So, X0, how much will be that? X0, it will be Xn Wn. See, this was e to the power minus j 2 pi by n into k into n, is it not? If you look at it, we were multiplying by e to the power minus j omega n into xn, is it not summation like this? And what is it? Xn e to the power minus j omega k into n. And what is omega k? Which means e to the power minus j 2 pi by capital N into k, is it not? K equal to 1 corresponds to this, k equal to 2, k equal to 0, k equal to 3, 4, 5, 6, 7. So, there are 8 values. So, we are taking different values of k between 0 and 7. Okay. There are 8 points. So, if you substitute here, so Wn into nk, which means e to the power minus j 2 pi by n into k into n. So, basically this reduces to wk into n, and wk is nothing but 2 pi by n into e to the power minus j 2 pi by n into k, okay, this small w. So, this is x n w n n k, is that okay? And this is to be evaluated at k equal to 0 to get this value, okay. So, what is it? If I put k equal to 0, this will be always 1, e to the power minus j 2 pi by n multiplied by 0 is always 1. So, it will be just summation of x n, sum of these terms, alright. So, it will be 1 minus 1 0, 2 plus 3 5 plus 1 6 7 9, is that okay? So, let us compute 1 or 2 more, then we will go to the details of this. What will be x 1 for the same sequence? What will be x 1? It will be x 0 plus x 1 into e to the power minus j 2 pi by 8 into 1 into 1 n into k, alright. N is this, k is this. So, when I am going to compute for k, I will multiply by this plus x 2 into e to the power minus j 2 pi by 8 into 2 into 1 plus x 3 into e to the power minus j 2 pi by 8 into 3 into 1. Is that all right? And so on, plus x 7 into e to the power minus j 2 pi by 8 7 into 1, okay. So, 1 comes every time because I am evaluating it for k equal to 1, that is corresponding to k, and this 7 3 2 etc., they will be coming along with the term x n, alright, because that n is varying. So, it is summated over n. So, how does it look like? 1 plus, first one is 1, then minus 1, next value is minus 1 into e to the power minus j. Now, there is a common multiplier that you can see, e to the power minus j 2 pi by 8 into 1. So long as this is 1, e to the power minus j 2 pi by 8 into 1, 2 pi by 8 into 1. So, e to the power minus j 2 pi by 8 is a basic element of rotation minus 45 degrees, and it is to be multiplied by 1 2 3 depending on the sequence element x 2 x 3 and so on. So, the first element it will be e to the power minus j pi by 4, okay. Then 2 into e to the power minus j 2 times this plus 3 into e to the power minus j 3 times this is the basic angle, plus 0 plus 1 into e to the power minus j 5 pi by 4 plus 2 into e to the power minus j 6 pi by 4 plus 1 into e to the power minus j 7 pi by 4. Is that all right? Whatever be that result, sum a plus j b you can write, all right. If I go for, say, I want to compute x 3, what should I do? I am arbitrarily taking some value other than 1 to make my point clear. X 0 plus what should be the multiplication of x 1? Now, the basic angle will be 3 times pi by 4, that is minus 45, minus 90 and then minus 135 degrees, okay. It is minus 135 degrees from your side, minus 135 degree should be the basic angle, and multiples of minus 135 degrees. Is that all right? So, x1 into, if you permit me to write in terms of degrees, which you are probably all convenient with, minus 135 degrees, I will write like this only for ease of understanding. Then x2 into e to the power minus j 270 degrees, all right, plus x3 into e to the power minus j 405 degrees, and so on. Is that okay? And you compute the values. For minus 45 degrees it is plus 0.707 minus j 0.707. For 90 degrees it will be just j. 135 degrees it is in the third quadrant, both will be negative. All the time it will be 1 by root 2. Then if I take x4, what will be the basic angle? 4 times 45 degrees. So 180. So it will start with minus 1, 2 times 180 plus 1, 3 times 180 minus 1, again 4 times 180 plus 1, and so on. So when we compute x4, which is half of capital N, that is 8 point sequence, if you take half of it, the basic angle will be 180 degrees, all right. So alternately the signs will be changing, okay. So if I ask you to compute x4, blindly you can write 1 minus of this, which is plus 1, minus then plus of 2, minus of 3, plus of 0, minus of 1, plus of 2, minus of 1, that will be the net result. So whenever you are going to compute x at n by 2, the sequence will be just alternately appearing with a negative sign, and so on. Is that okay? The reverse relation, that is to get xn from xk, is also very simple. It is 1 by n xk Wn minus nk. See, the forward sequence was xk sigma x small x n Wn nk. Mind you, W has associated with it a negative power here, all right, minus j 2 pi by n. So this means plus j 2 pi by n, okay. If you are given this set of xk, 8 discrete Fourier transforms, if I give you, you can always get back xn. Earlier you, for the continuous domain, you are integrating from minus pi to plus pi. Here you do not have to do that, you just take summation of those 8 points and you have to multiply by just complex conjugate. You see, earlier it was minus pi by 4, now if I put a power of plus 1, it will be plus pi by 4, all right. So it will be just complex conjugate. So W n n k is nothing but W n minus n k conjugate, all right. It is just a complex operator. Now how do you get this? Where is the proof? So let us go for the proof. So xk is, n varies from 0 to n minus 1. I can write xn Wn nk, n varying from 0 to n minus 1. Now this xn we have written as 1 by n x, say p, I can write xp Wn minus p k. Okay. P varying from, this is n equal to 0 to n minus 1. I should write p n w minus n k, okay, plus n k. Is that all right? See, x n, x k, I have started off with this, x k is equal to x n w n n k, and x n I can write in terms of this. I am not using the same variable k, I am taking, I can have any running variable k, so I have taken p, okay, x p w n p k, it should be p n, all right, and w n k, okay, p equal to 0 to n minus 1 without loss of generality. P is the running variable, so summated from this range 0 to n minus 1. Okay. K is not a running variable, k is at a particular value k you are evaluating, and over this again I am having a running variable of n. I can interchange p and n summation n equal to 0 to n minus 1, okay. I can put x p outside, w n into k minus p, okay, n is varying. Now, most of you have studied in 3-phase power systems balanced and unbalanced voltages, all right. Any unbalanced system we can always represent in terms of sequence components of 3 sets of balanced voltages, all right. So, if you remember, the matrix of transformation that we used was having an angular shift of 120 degrees, okay. We are writing that as an operator A, okay. So, we had a to the power 0, a to the power 1 and a to the power 2, where a cubed was making 1, all right. So, a was basically e to the power j 2 pi by 3, 120 degrees shift, we are multiplying in the positive direction. So, a 0 means 1, this was a, this was a square, all right. Now, you take any one of them, a to the power any of them, okay, and if you sum them together, that is a, suppose I take a basic element of a1, then a1 to the power 0 plus a1 to the power 1 plus a1 to the power 2 will be equal to 0. a2 to the power 0 plus a2 to the power 2 plus a2 to the power 1 plus a to the power 2 0. So, by the extend that same logic here, you will find Wn is a basic element, all right. If you take any difference k minus p other than 0, now if I take a0 to the power 0 plus a0 to the power 1 plus a0 to the power 2, then I will get 3, all right. So, it is basically the same thing, that is how you get the 0 sequence component, is it not? Wn is e to the power j 2 pi by n, okay. Now, if I multiply by n and sum it over n of a quantity other than 0, if k minus p is other than 0, 1, 2, 3, 4, whatever you take, if you sum it, it will be always equal to 0, but at k equal to p, it will be equal to n, it has come to 3, is it not? So, it will be equal to n. So, this n will get cancelled with this and this will stay only for k equal to p, is that all right? So, it becomes only xp, after summation it becomes only 1, 1 into n, n gets cancelled. So, we get xk is equal to x p, where p is equal to k. This is valid only for p equal to k. Okay. So, basically 1 plus w squared plus w cube and so on, w n minus 1 is always 0, sum of these will be always 0. If you take 1 plus w square plus w square squared, w squared cubed, w square to the power n minus 1 will be also equal to 0. You take any power of w as a basic element and then you add up these terms, it will be always equal to 0 except for w equal to w to the power 0. Okay. Now, there are certain interesting functions that we shall discuss now. Delta n, all right. What will be its DFT? What will be its DFT? Could someone suggest what will be the DFT of delta n? Delta n is basically a sequence like, suppose we have an 8-point sequence, we take only 8 points, then 1 0 0 0 0, there are 7 zeros, all right. So, if we have an 8-point DFT, what will be this? Okay, what is x0? 1, x1 1, x2 all will be 1. Okay, so xk equal to 1. This is what we have observed also in DTFT. You remember? What will be delta, say, n minus 3? What will be delta n minus 3? Okay. Delta n minus 3 is a sequence like 0 0 0 1, then again all zeros. Okay. So, what will be capital X0? 1, X1 W n 3. Do you all agree? What will be X2? What is W n 3? Minus 1 by root 2 minus j 1 by root 2, third quadrant, 135 degrees, is not. If n is equal to 8, you are considering an 8-point sequence, then it will be 135 degrees. And what will be x2? 2 times 135 degrees, so 270 degrees. So, minus 270 degrees, mind you, minus 270 is plus 90 degree, so that will be plus j. Okay, I will write Wn6, that is nothing but plus j. We have taken n is equal to, we should put 8, then will be clear. Yes, we are considering only 8-point sequence for ease of understanding. You change the value of n, obviously these values will be changing. Okay. So, this is how you can obtain the DFTs. There are now, can you compute DTFT from DFTs? That is, what we are trying to achieve is, if you are given say the DFTs, of course they are complex, there is an angle associated with that. Okay, I will show only the magnitudes on this side and so on. Suppose this is a DFT. What we are trying to find out is, what is that continuous function whose discrete values are these. That means we are trying to reconstruct, the original DTFT whose sampled values are these DFTs. So, from the sampled values we are trying to reconstruct the original DTFT. Okay. So, we go by this x e to the power j omega is sigma xn e to the power minus j n omega. Okay. And what is xn? We can write in terms of the DTFTs, the DTFT we can write in terms of DFT, it will be xk wn minus kn, all right, then e to the power minus j n omega. This is for xn from the discrete domain, is it not? I can take 1 by n outside, this is summated over k. I can interchange the summation operation and then xk summation. What is wn minus kn? We can write in terms of e to the power minus j 2 pi by n into k. Is this all right? This is minus, that means here it will be plus minus n omega. So, minus omega whole thing into n. Is that all right? Is this okay? N varying from minus. So, what you are adding up is capital N number of summation of these exponential terms, all right, for a particular value of omega. We are now trying to find out all continuous, the continuous domain representation of that frequency function. So, here if I take e to the power j 2 pi by n k minus omega as a basic element, say x, all right. So, what is this? 1 plus x squared, n is equal to 0, 1, 2, 3 means up to x to the power n minus 1. Okay. I can write this as multiply by 1 minus x, divide by 1 minus x. So, 1 minus x to the power n by 1 minus x, is it not? So, we can write this as equal to 1 by n summation xk, then 1 minus e to the power minus j omega. I can always take omega on this side. So, I put a minus 2 pi by n k, okay, whole to the power n divided by 1 minus e to the power minus j omega minus 2 pi by n into k. Correct me if I am wrong. K equal to 0 to n minus 1. Is that okay? I can write this. This divided by 2, if I take out, then it will be sine function. Similarly, 1 minus e to the power minus j theta, I can take minus j theta by 2 common. So, e to the power minus j theta by 2 into e to the power j theta by 2 minus e to the power minus j theta by 2, okay, which will give me e to the power minus j theta by 2 into twice sine of theta by 2 into j. Okay. Now, both of them will generate j, so they will get cancelled. Both of them will generate 2, so they will also get cancelled. So, 2j will get cancelled from both. So, I will take out 1 by n sigma xk e to the power minus j omega minus 2 pi by n k into n by 2 divided by e to the power minus j omega minus 2 pi by n k divided by 2, and this side I will have sine of omega minus, okay, if I call this as theta, okay, 2 pi by n k into n by 2 divided by sine of omega minus 2 pi by n k divided by 2, okay, this angle divided by 2. So, that gives me 1 by n in a compact form. If I write x k e to the power minus j, this is this by 2 if I take as theta, omega minus 2 pi by n k by 2 as theta, then it is n theta and this is theta. So, n minus 1 into theta e to the power j theta 1 e to the power j theta 2. So, it will be theta 1 minus theta 2, okay, into sine of n theta by 2 by sine of theta by 2, where or this I have taken as theta. So, sin n theta by sin theta, okay. So, given the values of x k, you can always reconstruct capital X e to the power j omega. The other alternative is this will be giving you an analytical expression, all right. So, that anybody can put in any value of omega, he can evaluate this. Corresponding to omega, you have to evaluate theta and then he can make a program. So, normally what we do, we do not make an analog plot, we take large number of points. No? Say if I ask you to sketch x versus omega, capital X versus omega like this, what you do? You compute for omega equal to 0.001 radian, 0.002 radian and so on, large number of points you compute and then you sketch it, is it not? So, if you have to do it for getting a continuous domain function, if you have to do it in a discrete way, then why not do it with the help of DFT. So, what you do, suppose there are 8 points given to you. So, 8 points will give you this kind of a characteristic, out of which you are trying to identify with those 8 points. If you take direct DFT, you get only 8 points here, okay. Instead of 8 points, I could have selected 16 points, all right. 16 points and I could have got 16 such values. So, x0, x1 up to x7, there are 7 points given to you. There is no harm if I put some more zeros, 8 more zeros. So, that becomes a 16 point sequence. Okay. Now, my multiplier will be e to the power minus j 2 pi by 16, the basic element will be 2 pi by 16, 22.5 degrees. I will keep on doing that and then I will get 16 components, alright. If I append it with say large number of zeros to make it length of 256, then I will get 256 such points, alright. So, basically you append this by zeros to make it of a length m, which is much greater than the given sequence length n. Well, I am getting large number of points, I can get a very smooth curve. So, my idea is to get DTFT from DFT. One is using this relationship, alright, but then this will remain, in any case this will remain only on paper as an analytic function, as an algebraic expression, but when you want to compute it, for making a plot you take discrete points and compute, is it not, compute these values and then you make a plot. So, when you are going to take discrete points, that means what values of theta will you take, what values of omega will you take, say 0.01, 0.02, 0.03, so many radians. So, I suggest you take 1000 such points, 1024 points, 2 pi divided by 1024, that will also give you of that order 0.01, 0.02, is it not. So, if I can take 1024 points, that means these 8 points I append with zeros to make it a length of 1024, then I will get those 10 to 24 points by a direct computation of DFT. Now, if a faster algorithm exists for computation of the DFT for large number of points, where number of points is 2 to the power n, then the problem is very simple, alright. So, that algorithm is known as FFT. So, fast Fourier transform, basically the discrete Fourier transform is computed by a very fast algorithm. So, fast Fourier transform is not something different, it is only an algorithm. So, whenever you are asked to compute the DFTs of sequence, we normally pad it with zeros, alright, we get large number of points and we try to take the advantage of FFT algorithm, that is very simple. So, we go for appending, also known as padding, appending the data or the sequence xn by zeros. Sequence length was n and m is the appended sequence length. Okay. So, m is much greater than n. So, this is the practical way of computing DFT from DTFT. Now, there are certain important properties of DFT that we can just discuss. The properties are, most of the properties are same as DTFT. Okay. Most of the properties are similar to DTFT. There are some interesting features of DFT. Circular time shifting. Now, while computing DFT, when we talk about DFTs, we introduce this term circular sequence. Suppose we have a sequence say 0, 1, 2, 3, 4 like this. I mark it 0, 1, 2, 3, 4, 5, then suppose 0, 1, 2, 3, 4, 5. This is a 5-point sequence. I have not shown you the values for which a particular variable say xn exists. That is x0 is say plus 3, okay, x1 may be 4, x2 may be 1 and so on. There are some values at these points and after that the function becomes 0. This is a normal linear sequence. Okay. If we roll it, that is next point is made 0, that is this 0 is brought here next to 5, then what will you see? If I keep on shifting it, it will be periodically appearing, is it not? If I keep on rotating it, you will get 0, 1, 2, 3, 4, 5, 0, 1, 2, 3, 4, 4, 5 and so on. So, such a periodic sequence can be generated from any finite length sequence by just putting it like this, rolling it, alright, winding it, and then you get a sequence like this. Now, if I just move it, I will get the same sequence with different starting point, alright. So, this is known as a circular shift. I mean, this kind of a sequence we shall be using in circular shift property. So, circular time shifting property is, suppose there is a function f modulo n. Modulo n means basically 1, 2, 3, 4, 5, 6. This capital N is 6. So, after every 6 points it is repeated. Okay. So, if I take n is equal to 3, n is equal to 3 and n0 is any particular shift. So, 3 minus a n0 is 1. So, 3 minus 1 and then I keep on 4 minus 1, 7 minus 1, 8 minus 1 if I want to compute. 8 minus 1 if I take modulo, modulo means you subtract, keep on subtracting 6, alright. If it is in the negative region, then you keep on adding 6. So, x of minus 2 is same as if I add 6, x of 4, alright, is same as x of 10. So, f, if I evaluate this, the corresponding DFT will be W n k times n0 f, I am writing f k. So, if I want to compute the kth element of that shifted sequence, then it will be the original sequence value of f k multiplied by this W n k 0. Okay. We will stop here for today, we will take it up in the next class.